Let's look at graphing our basic trig functions. And we'll start off with the sine curve. We know it has an amplitude of 1, so I'll mark that in on the y-axis. And I'll mark off all the boundary values, and really the only difference to what we've done before, instead of marking it off in degrees, I'm marking it off in radians. We know the sine curve starts at the origin, it then goes up to its amplitude, and then that pattern of going down and up is repeated, and we get our lovely sine curve. What do we know about the sine curve? Domain therefore is all real x. The range is in between -1 and 1. We know it's an odd function. We've got the rotational symmetry, which would allow us to use this relationship. The sine of negative x is equal to the negative the sine of x. We also have this thing called period. Period is how long does it take until it starts repeating. So how long until it's in the same position. Now, not only is it in the same position, but going in the same direction. So I'm at one of both of those. The reason I say that, I guess, is because if you look at the x-intercepts, it looks like, well, it's only pi until I get to the same point. But at the origin I'm going up, whereas at pi I'm going down. So it has to be going in the same direction as well. So our period is 2 pi. And amplitude, well, how far above and below its axis does it go? That's just 1. Cosine curve, so let's draw that one in. Again, amplitude is 1. Let's mark off our divisions. Cosine starts at the amplitude. I'll plot that one in first. And then it also has that pattern of going down and going up. So plot in our boundary values, which allows us then to draw in a nice cosine curve. And of course it is the sine curve translated, I was going to say 90 degrees, I suppose I should say pi on 2 radians, because we're talking about radians, because that's what cosine means. It's the complement of sine, and complementary angles of course add up to 90 degrees, or pi on 2 radians. As it is the same curve, domain is the same, all real x, range is the same, but this one is an even function. We've got that reflection symmetry. Therefore, we could use this feature, the cosine of negative x is equal to the cosine of x. Period is also 2 pi, amplitude stays at 1. Alright, oh yes, and so that's what I was saying about cosine being the complement of sine. So what we did with our sine curve, if we look at it, we could say, well, hang on, negative x, a function negative x means reflect in the y-axis, but then we've shifted it right pi on 2 units, and that's how we got our cosine curve. Let's look at the tan curve then. Wow, we don't really mark anything on the y-axis, but we do like to start our point at the origin, but the pattern for the tan goes x-intercept, asymptote, x-intercept, asymptote, x-intercept, asymptote, and so on and so on and so on. We know we have to go through the x-intercepts, we have to bend towards the asymptotes. We also know which quadrants we're positive in, and so on, which allows us to get that nice curve. Reminder, it's not a cubic you're drawing in, it's a tan curve. It should go through at an angle of 45 degrees, unlike the cubic which has a horizontal tangent. This one's at 45 degrees. Repeat that between all the asymptotes, and there's our tan curve. The main, little bit more involved to write down because of all these asymptotes. Probably the simplest way of doing it is saying, well look, my first one is at pi on 2, and then I know every multiple of pi after that and before that we would also have an asymptote. No, it's all real x except for those asymptotes. Range, all real y. It's an odd function, rotational symmetry. So therefore we could use the fact that the tan of negative x is equal to the negative tan of x. Its period is pi. So unlike the sine and cosine curve, this one repeats every pi radians. Right, let's do one of the reciprocal ones. Cosecant, which is the reciprocal of sine. Now the basic curve, sine x, this is what we're going to do with it. We're going to take the reciprocal of it, and the idea when we drew reciprocal graphs, okay, we knew x-intercepts will become asymptotes. Draw those in. 1 was an important point, because if you turn 1 upside down, you get 1. Same with negative 1, so I'll plot those points in. Now that pretty much completes it, because the other things we know were the sign's not going to change, and where the original graph was below 1, the new graph will be above 1. Where the original graph was increasing, the new one is decreasing, all those sorts of things. So there is our cosecant curve. 11J. Let's play. Oh, that rhymes.